Cryptography is the practice of developing and using coded algorithms to protect and obscure transmitted information so that it may only be read by those with the permission and ability to decrypt it. Put differently, cryptography obscures communications so that unauthorized parties are unable to access them. Cryptography definition is the art of keeping information secure by transforming it into form that unintended recipients cannot understand. In cryptography, an original human-readable message, referred to as plain text, is changed by means of an algorithm, or series of mathematical operations, into something that to an uninformed observer would look like gibberish. This gibberish is called ciphertext. Cryptographic systems require some method for the intended recipient to be able to make use of the encrypted message, usually, though not always, by transforming the ciphertext back into plain text. Cryptography versus cryptology versus encryption. Before we move into the meat of this article, let's define a couple terms related to cryptography. The syllable crypt may make you think of tombs, but it comes from a Greek word that means hidden or secret. Cryptography literally means secret writing. Cryptology, meanwhile, means something like knowledge of secrecy. If cryptography is the practice of writing secret messages, then cryptology is the theory, although the two words are often used interchangeably. Encryption, making secret, is what we call the process of turning plain text into ciphertext. Encryption is an important part of cryptography, but doesn't encompass the entire science. Its opposite is decryption. One important aspect of the encryption process is that it almost always involves both an algorithm and a key. A key is just another piece of information, almost always a number, that specifies how the algorithm is applied to the plain text in order to encrypt it. In a secure cryptographic system, even if you know the method by which some message is encrypted, it should be difficult or impossible to decrypt without that key. Keep algorithms and keys in your mind, because they'll be important as we move on. History of cryptography. This is all very abstract, and a good way to understand the specifics of what we're talking about is to look at one of the earliest known forms of cryptography. It's known as the Caesar cipher, because Julius Caesar used it for his confidential correspondence. As his biographer Suetonius described it, if he had anything confidential to say, he wrote it in cipher, that is, by so changing the order of the letters of the alphabet. If anyone wishes to decipher these, and get at their meaning, he must substitute the fourth letter of the alphabet, namely D, for A, and so with the others. Suetonius's description can be broken down into the two cryptographic elements we've discussed, the algorithm and the key. The algorithm here is simple: each letter is replaced by another letter from later in the alphabet. The key is how many letters later in the alphabet you need to go to create your ciphertext. It's 3 in the version of the cipher Suetonius describes, but obviously other variations are possible. With a key of 4, A would become E, for instance. A few things should be clear from this example. Encryption like this offers a fairly simple way to secretly send any message you like. Contrast that with a system of code phrases where, say, "Let's order pizza" means I'm going to invade Gaul. To translate that sort of code, people at both ends of the communication chain would need a book of code phrases, and you'd have no way to encode new phrases you hadn't thought of in advance. With the Caesar cipher, you can encrypt any message you can think of. The tricky part is that everyone communicating needs to know the algorithm and the key in advance, though it's much easier to safely pass on and keep that information than it would be with a complex code book. The Caesar cipher is what's known as a substitution cipher, because each letter is substituted with another one. Other variations on this, then, would substitute letter blocks or whole words. For most of history, cryptography consisted of various substitution ciphers deployed to keep government and military communications secure. Medieval Arab mathematicians pushed the science forward, particularly the art of decryption. Once researchers realized that certain letters in a given language are more common than others, it becomes easier to recognize patterns, for instance. But most pre-modern encryption is incredibly simple by modern standards, for the obvious reason that, before the advent of computers, it was difficult to perform mathematical transformations quickly enough to make encryption or decryption worthwhile. In fact, the development of computers and advances in cryptography went hand in hand. Charles Babbage, whose idea for the difference engine presaged modern computers, was also interested in cryptography. During World War II, the Germans used the electromechanical Enigma machine to encrypt messages and, famously, Alan Turing led a team in Britain that developed a similar machine to break the code, in the process laying some of the groundwork for the first modern computers. Cryptography got radically more complex as computers became available, but it remained the province of spies and generals for several more decades. Principles of cryptography. Before we move on here to modern cryptography, let's pause to discuss two important principles that underlie it. The first is what's come to be known as Kirchhoff's principle, named after the 19th century Dutch cryptographer Auguste Kirchhoffs. Remember, as we said, any cryptographic system involves both an algorithm and a key. Kirchhoffs believed that a cryptographic system should be secure even if everything about the system, except the key, is public knowledge. Now, these were the days when cryptography had almost entirely military applications. The idea here is that, while it would be nice to keep your cryptographic system a secret, your opponent will almost certainly eventually figure it out. Claude Shannon, a World War II cryptographer who would go on to be a pioneer in information theory, put it more succinctly: the enemy knows the system. What Kirchhoffs and Shannon are getting at is that you want to design an algorithm that doesn't need to be a secret in order to successfully conceal information. That said, in today's world, the public nature of cryptographic algorithms is seen as something good in and of itself, rather than an unavoidable evil. Standard cryptographic algorithms have been widely studied and stress-tested, and trying to come up with your own private algorithms is doomed to failure, as security through obscurity usually is. What you do need to keep secret is your cryptographic key. We'll get to the mathematics of how that works in a moment, but for now, we'll touch on another cryptographic principle that makes that math possible: a reliance on one-way functions, mathematical operations that are very difficult to reverse. The classic example of a one-way function is the multiplication of two very large prime numbers together. While that calculation is simple to do, if you only had the end result, it would be very difficult, verging on impossible, to figure out the original two prime numbers. The question of whether any function can truly be one-way is debated by mathematicians, but many are irreversible in practice at the limits of our current computing power, so we'll leave that question aside as we move on. Cryptography in network security. It was the formation of the first computer networks that started civilians thinking about the importance of cryptography. Computers were talking to each other over the open network, not just via direct connections to one another. That sort of networking was transformative in many great ways, but also made it trivially easy to snoop on data traveling across the network. And with financial services being an early use case for computer communication, it was necessary to find a way to keep information secret. IBM led the way in the late 1960s with an encryption method known as Lucifer, which was eventually codified by the U.S. National Bureau of Standards as the first data encryption standard, DE. As the Internet began to grow in importance, more and better encryption was needed, and today a significant portion of data flying around the world is encrypted using varying techniques that we'll discuss in more detail in a moment. What is cryptography used for? We've already discussed some of the specific applications of cryptography, from keeping military secrets to transmitting financial data safely across the Internet. In the bigger picture, though, there are some broad cybersecurity goals that we use cryptography to help us achieve, as cybersecurity consultant Gary Kessler explains. Using cryptographic techniques, security pros can keep the contents of data confidential, authenticate the identity of a message's sender and receiver, ensure the integrity of the data, showing that it hasn't been altered, demonstrate that the supposed sender really sent this message, a principle known as non-repudiation. You may recognize some of these principles from variations of the CIA triad. The first of these uses is the obvious one: you can keep data secret by encrypting it. The others take a bit of explanation, which we'll get into as we describe the different types of cryptography. What are the types of cryptography? There are numerous cryptographic algorithms in use, but in general they can be broken into three categories: symmetric cryptography, asymmetric cryptography, and hash functions. Each has its own role to play within the cryptographic landscape. Symmetric cryptography. The Caesar cipher we discussed above is a great example of symmetric cryptography. In the example we used, if encrypted messages were being exchanged between Caesar and one of his centurions, both parties would have to know the key in this case, how many letters forward or backwards in the alphabet you need to move to transform plain text to ciphertext or vice versa. That's what makes it symmetrical. But the key needs to stay a secret between the two of them, which is why this is sometimes also called secret key cryptography. You couldn't send a key along with the message, for instance, because if both fell into enemy hands the message would be easy for them to decipher, defeating the whole purpose of encrypting it in the first place. Caesar and his centurion would presumably have to discuss the key when they saw each other in person, though obviously this is less than ideal when wars are being fought over long distances. Symmetric cryptography is widely used to keep data confidential. It can be very useful for keeping a local hard drive private, for instance, since the same user is generally encrypting and decrypting the protected data, sharing the secret key is not an issue. Symmetric cryptography can also be used to keep messages transmitted across the internet confidential. However, to successfully make this happen, you need to deploy our next form of cryptography in tandem with it. Asymmetric cryptography. Caesar may have been able to confer with his centurions in person, but you don't want to go into your bank and talk to the teller just to learn what the private key is for encrypting your electronic communication with the bank. That would defeat the purpose of online banking. In general, in order to function securely, the internet needs a way for communicating parties to establish a secure communications channel while only talking to each other across an inherently insecure network. The way this works is via asymmetric cryptography, which is sometimes called public key cryptography. In asymmetric cryptography, each participant has two keys. One is public and is sent to anyone the party wishes to communicate with. That's the key used to encrypt messages. But the other key is private, shared with nobody, and it's necessary to decrypt those messages. To use a metaphor, think of the public key as opening a slot on a mailbox just wide enough to drop a letter in. You give that key to anyone who you think might send you a letter so they can open the slot and deliver the envelope. The private key is what you use to open the mailbox so you can get the letters out. The mathematics of how you can use one key to encrypt a message and another to decrypt it are where the idea of one-way functions that we discussed above come into play. The two keys should be related to each other mathematically such that it's easy to derive the public key from the private key but not vice versa. For instance, the private key might be those two very large prime numbers, which you'd multiply together to get the public key. The InfoSec Institute has a deep dive if you're interested. The computations needed for asymmetric cryptography are much more complex and resource-intensive than those behind symmetric infrastructure. Fortunately, you don't need to use it to protect every message you send online. Instead, what usually happens is that one party will use symmetric cryptography to encrypt a message containing yet another cryptographic key. This key, having been safely transmitted across the insecure internet, will then become the private key that encodes a much longer communication session encrypted via symmetric encryption. In this way, asymmetric cryptography assists the cause of confidentiality. But these public keys are also part of a larger set of functions known as public key infrastructure, or PKI. PKI provides ways to be sure that any given public key is associated with a specific person or institution. A message encrypted with a public key thus confirms the identity of the sender, establishing authentication and non-repudiation. Hash functions. Symmetric and asymmetric cryptographic algorithms both involve transforming plain text into ciphertext and then back into plain text. By contrast, a hash function is a one-way encryption algorithm. Once you've encrypted your plain text, you can't ever recover it from the resulting ciphertext, referred to as a hash. Obviously, this too relies on one-way mathematical functions. This might make hash functions seem like a somewhat pointless exercise. But the key to their usefulness is that, for any given hash function, no two plain texts will produce the same hash. Mathematically, this isn't quite correct, but for any hash function actually in use, the chances of it happening are generally vanishingly small and can be safely ignored. This makes hashing algorithms a great tool for ensuring data integrity. For instance, a message can be sent along with its own hash. Upon receiving the message, you can run the same hashing algorithm on the message text. If the hash you produce is different from the one accompanying the message, you know the message has been modified in transit. Hashing is also used to ensure the confidentiality of passwords. Storing passwords as plain text is a big security no-no because that makes users prone to account and identity theft in the wake of data breaches, which sadly doesn't stop big players from doing it. If instead you store a hashed version of a user's password, hackers won't be able to decrypt it and use it elsewhere even if they do manage to breach your defenses. When a legitimate user logs in with their password, you can just hash it and check against the hash you have on file. Cryptography examples and techniques. There are numerous techniques and algorithms that implement each of the three types of encryption discussed above. They are generally quite complex and beyond the scope of this article. We've included links here where you can learn more about some of the most commonly used examples. Secret key encryption. TripleDA, the modern successor to the discussed above Advanced Encryption Standard, AES, Blowfish and its successor Twofish, both from security legend Bruce Schneier. Public key encryption. Diffie-Hellman key exchange. RSA Gamal hash functions. There is a wide range of hash functions with different specialized purposes. The list on Wikipedia is a good place to start. Is the art of keeping information secure by transforming it into form that unintended recipients cannot understand. In cryptography, an original human-readable message, referred to as plain text, is changed by means of an algorithm, or series of mathematical operations, into something that to an uninformed observer would look like gibberish. This gibberish is called ciphertext. Cryptographic systems require some method for the intended recipient to be able to make use of the encrypted message, usually, though not always, by transforming the ciphertext back into plain text. As the world becomes increasingly digital, the need for security has become ever more imperative. That's where cryptography and its applications to cybersecurity come in. Essentially, the word refers to the study of secure communications techniques, but cryptography is closely associated with encryption, or the act of scrambling ordinary text into what's known as ciphertext and then back again into ordinary text, called plain text, when it arrives at its destination. Several historical figures have been credited with creating and using cryptography through the centuries, from Greek historian Polybios and French diplomat Blaise de Vigenère to Roman Emperor Julius Caesar, who is credited with using one of the first modern ciphers, and Arthur Scarbius, who created the Enigma code-breaking machine during World War II. Likely, none of them would recognize the ciphers of the 21st century. But exactly what is cryptography? And how does it work? Cryptography definition. Cryptography is the technique of obfuscating or coding data, ensuring that only the person who is meant to see the information, and has the key to break the code, can read it. The word is a hybrid of two Greek words, kryptos, which means hidden, and graphein, which means to write. Literally, the word cryptography translates to hidden writing, but in reality, the practice involves the secure transmission of information. The use of cryptography can be traced to the ancient Egyptians and their creative use of hieroglyphics. But, the art of coding has seen great strides over the millennia, and modern cryptography combines advanced computer technology, engineering, and maths among other disciplines to create highly sophisticated and secure algorithms and ciphers to protect sensitive data in the digital era. For example, cryptography is used to create various types of encryption protocols that are regularly used to protect data. These include 128-bit or 256-bit encryption, secure sockets layer, SSL, and transport layer security, TLS. These encryption protocols protect all manner of digital information and data, from passwords and emails to ecommerce and banking transactions. There are different cryptographic types, which are useful for different purposes. For example, the simplest is symmetric key cryptography. Here, data is encrypted using a secret key, and then both the encoded message and the secret key are sent to the recipient for decryption. Of course, the problem here is that if the message is intercepted, the third party can easily decode the message and steal the information. To create a more secure system of encoding, cryptologists devised asymmetric cryptography, which is sometimes known as the public key system. In this instance, all users have two keys, one public and one private. When creating a coded message, the sender will request the recipient's public key to encode the message. This way, only the intended recipient's private key will decode it. This way, even if the message is intercepted, a third party cannot decode it. Why is cryptography important? Cryptography is an essential cybersecurity tool. Its use means that data and users have an additional layer of security that ensures privacy and confidentiality and helps keep data from being stolen by cybercriminals. In practice, cryptography has many applications. Confidentiality: only the intended recipient can access and read the information, so conversations and data remain private. Integrity of data: cryptography ensures that the encoded data cannot be modified or tampered with en route from the sender to the receiver without leaving traceable marks. An example of this is digital signatures. Authentication: identities and destinations, or origins, are verified. Non-repudiation: senders become accountable for their messages since they cannot later deny that the message was transmitted. Digital signatures and email tracking are examples of this. What is cryptography in cybersecurity? Interest in the use of cryptography grew with the development of computers and their connections over an open network. Over time, it became obvious that there was a need to protect information from being intercepted or manipulated while being transmitted over this network. IBM was an early pioneer in this field, releasing its Lucifer encryption in the 1960s. This eventually became the first data encryption standard, DE. As our lives become increasingly digital, the need for cryptography to secure massive amounts of sensitive information has become even more imperative. Now, there are many ways in which cryptography is crucial in the online space. Encryption is an essential part of being online, since so much sensitive data is transmitted every day. Here are a few real-life applications. Using virtual private networks, VPNs, or protocols such as SSL to browse the internet safely and securely. Creating limited access controls so that only individuals with the correct permissions can carry out certain actions or functions, or access particular things. Securing different types of online communication, including emails, login credentials, and even text messages such as with WhatsApp or Signal through end-to-end encryption. Protecting users from various types of cyber attacks, such as man-in-the-middle attacks. Allowing companies to meet legal requirements, such as the data protections set out in the General Data Protection Regulation, GDPR. Creating and verifying login credentials, especially passwords. Allowing the secure management and transaction of cryptocurrencies. Enabling digital signatures to securely sign online documents and contracts. Verifying identities when logging into online accounts. What are the types of cryptography? Cryptography definitions are, understandably, quite broad. This is because the term covers a wide range of different processes. As such, there are many different types of cryptographic algorithms, each one offering varying levels of security, depending on the type of information being transmitted. Below are the three main cryptographic types. Symmetric key cryptography: this simpler form of cryptography takes its name from the fact that both the sender and receiver share one key to encrypt and decrypt information. Some examples of this are the Data Encryption Standard, DE, and Advanced Encryption Standard, AES. The main difficulty here is finding a way to securely share the key between the sender and receiver. Asymmetric key cryptography: A more secure type of cryptography, this involves both the sender and receiver having two keys, one public and one private. During the process, the sender will use the receiver's public key to encrypt the message, while the receiver will use their private key to decrypt it. The two keys are different, and since only the receiver will have the private key, they will be the only ones able to read the information. The RSA algorithm is the most popular form of asymmetric cryptography. Hash functions, these are types of cryptographic algorithms that do not involve the use of keys. Instead, a hash value, a number of fixed lengths that acts as a unique data identifier, is created based on the length of the plain text information and used to encrypt the data. This is commonly used by various operating systems to protect passwords, for example. From the above, it is clear that the main difference in symmetric and asymmetric encryption in cryptography is that the first only involves one key while the second requires two. Types of symmetric cryptography. Symmetric encryption is sometimes called secret key cryptography because one single purportedly secret key is used to encrypt and decrypt information. There are several forms of this type of cryptography, including stream ciphers. These work on a single byte of data at a time and regularly change the encryption key. In this process, the key stream can be in tandem with or independent of the message stream. This is called self-synchronizing or synchronous, respectively. Block ciphers. This type of cryptography, which includes the Feistel cipher codes and decodes one block of data at a time. Forms of asymmetric key cryptography. Asymmetric cryptography, sometimes referred to as public key encryption, hinges on the fact that the receiver has two keys in play, a public one and a private one. The first is used by the sender to encode the information, while the receiver uses the latter, which only they have to securely decrypt the message. Asymmetric key cryptography encrypts and decrypts messages using algorithms. These are based on various mathematical principles, such as multiplication or factorization, multiplying two big prime numbers to generate one massive, random number which is incredibly tricky to crack, or exponentiation and logarithms, which create exceptionally complex numbers that are nearly impossible to decrypt, such as in 256-bit encryption. There are different types of asymmetric key algorithms, such as RSA, the first type of asymmetric cryptography to be created. RSA is the basis of digital signatures and key exchanges, among other things. The algorithm is based on the principle of factorization. Elliptic curve cryptography, ECC, often found in smartphones and on cryptocurrency exchanges. ECC employs the algebraic structure of elliptic curves to build complex algorithms. Significantly, it does not require much storage memory or usage bandwidth, making it especially useful for electronic devices with limited computing power. Digital signature algorithm, DSA, built on the principles of modular exponentiations. DSA is the gold standard for verifying electronic signatures and was created by the National Institute of Standards and Technologies. Identity-based encryption, IBE. This unique algorithm negates the need for a message recipient to provide their public key to the sender. Instead, a known unique identifier such as an email address is used by the sender to generate a public key to encode the message. A trusted third-party server then generates a corresponding private key that the receiver can access to decrypt the information. Cryptographic attacks. As with most technologies, cryptography has become increasingly sophisticated. But that does not mean that these encryptions cannot be broken. If the keys are compromised, it is possible for an external party to crack the coding and read the protected data. Here are a few potential issues to watch for. Weak keys. Keys are a collection of random numbers used with an encryption algorithm to alter and disguise data so that it is incomprehensible to others. Longer keys involve more numbers, making them much trickier to crack and therefore, better for protecting data. Using keys incorrectly. Keys need to be used correctly. If they are not, hackers can easily crack them to access the data they are supposed to protect. Reusing keys for different purposes, like passwords. Each key should be unique. Using the same key across different systems weakens the ability of cryptography to protect data. Not changing keys. cryptographic keys can quickly become out of date, which is why it is important to regularly update them to keep data secure. Not storing keys carefully. Ensure that keys are kept in a secure place where they cannot easily be found, otherwise they can be stolen to compromise the data they protect. Insider attacks. Keys can be compromised by individuals who legitimately have access to them, such as an employee, and who themselves them on for nefarious purposes. Forgetting the backup. Keys should have a backup because if they suddenly become faulty, the data they protect could become inaccessible. Recording keys incorrectly. Manually entering keys into a spreadsheet or writing them down on paper may appear to be a logical choice, but it is also one that is prone to error and theft. There are also specific cryptography attacks designed to break through encryptions by finding the right key. Here are some of the common brute force attacks, broad attacks that try to randomly guess private keys using the known algorithm. Ciphertext-only attacks. These attacks involve a third party intercepting the encrypted message, not the plain text, and trying to work out the key to decrypt the information, and later, the plain text. Chosen ciphertext attack. The opposite of a chosen plain text attack. Here, the attacker analyzes a section of ciphertext against its corresponding plain text to discover the key. Chosen plain text attack. Here, the third party chooses the plain text for a corresponding ciphertext to begin working out the encryption key. Known plain text attack. In this case, the attacker randomly accesses part of the plain text and part of the ciphertext and begins to figure out the encryption key. This is less useful for modern cryptography as it works best with simple ciphers. Algorithm attack. In these attacks, the cybercriminal analyzes the algorithm to try and work out the encryption key. Is it possible to mitigate the threat of cryptography attacks? There are a few ways in which individuals and organizations can try and lower the possibility of a cryptographic attack. Essentially, this involves ensuring the proper management of keys so that they are less likely to be intercepted by a third party, or usable even if they do. Here are a few suggestions. Use one key for each specific purpose. For example, use unique keys for authentication and digital signatures. Protect cryptographic keys with stronger key encryption keys, KEKs. Use hardware security modules to manage and protect keys. These function like regular password managers. Ensure that keys and algorithms are regularly updated. Encrypt all sensitive data. Create strong, unique keys for each encryption purpose. Store keys securely so they cannot be easily accessed by third parties. Ensure the correct implementation of the cryptographic system. Include cryptography in security awareness training for employees. The need for cryptography. Most people will not need to have more than a basic understanding of what cryptography is. But learning the cryptography definition, how the process works, and its applications to cybersecurity, can be useful in being more mindful about managing day-to-day digital interactions. This can help most people keep their emails, passwords, online purchases, and online banking transactions, all of which use cryptography in their security features, more secure. Thank you for watching this video.